Dear students, this is the first lecture in our Chemistry of Life series, and I will be going over the elements of life and chemical bonds. I have also listed here in gray the 6 most common elements that you will find in life. So there is an extra credit assignment that covers about 4 of these chemicals' basic properties, so you can do that if you want to get a more in-depth look at these elements. But let's go ahead and get started. First, we're going to be covering these topics in the elements of life. We'll discuss what are atoms and what they're made of. Then we're going to look at a special type of atoms known as isotopes. Then we're going to look at those 6 elements we talked about before very quickly. Then we'll discuss what are ions. And finally, we will end with the property that governs ions, isotopes, and atoms' electronegativity, and this will lead us right into understanding chemical bonds. So first of all, what are atoms? Well, all living and non-living things are made up of matter, which is a physical substance, okay? So all things in the universe have matter in it except for energy, which is matterless. Now, if you look here at this picture at the bottom that my mouse is hovering over, this is actually a photo from a microscope that was able to capture in these little dots that the arrows are pointing to different atoms of hydrogen, which is an element that we'll discuss in a moment. So atoms are, even though we haven't really been able to see them for a long time, they're not a new idea. They were first proposed by a Greek philosopher thousands and thousands of years ago who was named Democritus. And he believed that they were just these indestructible little balls, which are not true, but it's okay. That was thousands and thousands of years ago. So atoms are organized in different elements, which are the purest forms of matter, and these elements are arranged in the periodic table. In this link over here, if you're interested to learn more about the history of the periodic table, you can watch this short little video. So all of the elements that humans know of are organized in this table of elements. So the ones that we care the most about, I'm just going to very briefly circle. So we deal a lot with hydrogen, we deal a lot with carbon, nitrogen, oxygen. We see a little bit of sulfur and phosphorus, but mainly these 4 elements I've circled are the ones that you are going to see pop up a lot in this class. So it's really amazing that even though there's like maybe 108 plus elements that we know of, pretty much all of chemistry and biology boils down to those 6 elements, which is both really cool and probably boring if you love chem. So what are atoms made up of? They're made up of 3 subatomic particles. We have protons, which have a positive charge, so these are like the happy-go-lucky people in our classroom. Okay. Then we have the electrons, which have a negative charge. So these are like our Debbie Downers. If we have a Debbie, I'm sure you are definitely not a downer. You're a wonderful person. And then we have our neutrons, which are neutral. So these are like the meh, don't really care type of people. So the way that an atom is organized is that the protons and the neutrons are going to cluster together in a positively charged nucleus. This makes up the majority of an atom's mass, okay? This is a little different than a cell's nucleus because it's much smaller and not alive, but, it's central to the atom, so that's why it's in the middle, okay? The electrons, because they have a negative charge, they are attracted to the nucleus. So they are going to orbit it, almost like planets might be drawn by gravity to the sun, okay? So one important rule to keep in mind with chemistry is that opposites attract, okay? And you may have even heard that this is a good rule to keep in dating. However, I don't know if that's really a good idea because I'm sure that you will not be attracted to a person who is the complete opposite of you. Like, if you don't like to text and someone texts you every 20 seconds, that would probably be annoying, right? Well, what do I know? So one thing to keep in mind is that this model of the atom is actually pretty old. So whatever you will learn in chemistry will be the updated new model. As biologists, we don't care that much too deeply, but as long as you get the idea that the nucleus has a positive charge and you've got these negatively charged electrons that are orbiting it because they're attracted, you are good to go. Now, all atoms want to have a full valence shell. So they want to be content and happy. And what this means is that they want to have all electrons filled in their valence shell. So you might be looking at me like, what is this? What is this fancy word, valence? These are the outermost electrons, okay? And what this does is it helps to kind of shield the atom from any other positive and negative charges, okay? So here you can imagine is the nucleus, all right? And it's got a positive charge, and you're going to have the first shell that electrons will go into. So only 2 electrons can fit in the innermost shell because there's not a lot of space. Okay, so only 2 electrons can fit in here. All the other electrons are going to fit in the outer shells. So this one would probably be considered the valence shell. And because it's bigger, it can fit about 8 electrons, all right? I'm not going to go into why it can fit 8 electrons. That is more of a chemistry question. But you basically need to have about 8 electrons in order for this to be happy. So far we only have 7, so we're missing that 8. This would be a sad atom, okay? And the minute you put that other one in there, now it is happy. And when we say they're happy, not like a human emotion, but this means that they are not going to react. They are not going to react. So atoms are going to share, take, or lose electrons in order to get to a full valence shell. Okay? How do we figure out the number of electrons, protons, and neutrons that atoms have? We're going to need some information from the periodic table. So this is what we'd say is a periodic cell. So this is going to give us some information about the element nitrogen. So they're always going to have the element written in there. There's going to be a 1 to 2 letter symbol for that element. Here it's a capital N. And then there's going to be 2 facts that are important. So the atomic number and the atomic mass. The atomic number is the number of protons and electrons that you find in that element. So these are going to be equal. Okay, so nitrogen has 7 protons and 7 electrons. The atomic mass is basically the number of protons and neutrons. Don't worry about why it's not a whole number. That just has to do with the fact that there are different flavors of atoms and you have to take an average of them. So you'll learn more about why the atomic mass is not a whole number in chemistry. So how would you figure out the number of neutrons you have? Well, you would subtract the atomic number from the atomic mass. So here I'm going to draw that equation, the atomic mass, and you're going to subtract the atomic number. So in this case, we have 14.007. We're going to subtract 7 from it, and we have 7.007 neutrons. So there's no such thing as a 0.007 neutron, so we just write this as 7. Now, not all atoms are the same. They are all unique, just like you and me. And we call these different flavors or versions of an element's atom an isotope. So isotopes are basically the same for a particular element. That means they're going to act the same. So they would have the same number of protons and the same number of electrons, but they have a different number of neutrons. So that's why they're the same, because the neutrons, remember, have a neutral charge. So they will still act the same as any other atom of, nitrogen or oxygen. Okay. Now, some isotopes are radioactive. So, if you ever watched HBO Chernobyl, you probably know all about nuclear power and radioactivity, right? Well, hopefully. But in this case, when an isotope is radioactive, what this means is that the nucleus is unstable. So, typically, an unstable nucleus comes from having too many protons and neutrons. Okay, so it's a bit heavy. And it's going to eject some of the neutrons and protons in order to become more stable. When it does that, it releases bursts of energy. So sometimes the energy can be harmless, okay? So in the case of your bananas at home, they probably have radioactive potassium, but that does not release crazy amounts of energy, or else you probably wouldn't be eating bananas, okay? On the other hand, you can have some deadly energy. So, in the case of uranium 238, which was the main type of material used in nuclear reactors, when this decays, it's going to release gamma radiation, which is the highest form of radiation that we really have. And pretty much, if you're exposed to gamma radiation, unfortunately, you will not live. Now, we don't have to worry too much about isotope chemistry at all, except it's got some really important applications. So this is more what I want you to focus on, the contributions it has to biology. So we can use it to see how old some specimen are. We can also use it to detect DNA, proteins, and we can also use it to fight cancer. So it is used in chemotherapy, some forms of cobalt. Okay, so really isotope chemistry has some great applications to biology. And as long as you kind of understand that they're different flavors of the same element, you're good to go. Now let's talk about elements that are essential to life, because as I showed you earlier, there's only about 6 that we care deeply about, and they are known as SPONCH. So they are right here. This is sulfur, this is phosphorus, this is oxygen in the bubbles, this is liquid nitrogen. Don't really see that much of it naturally on the planet, but we do have a lot of nitrogen gas. This is carbon in its inorganic form, and then this right here is actually hydrogen gas. So together they make up Sponge, which is also a cookie that you can get in Smart and Final. I wouldn't really recommend it. It's got coconut, so it's a little interesting to me personally, but you may like it. And it makes up about 99% of all of the living mass of a human body. So it is ordered from least abundant to most abundant. So sulfur is the least abundant element in the human body, and hydrogen is the most abundant. So sponge, it's really important, and I have a little video that goes more in depth about these 4 elements right here. We don't really talk too much about sulfur and phosphorus in this class that you can do for the extra credit assignment. Okay, the next thing I'm going to talk to you about is ions, which are actually positively and negatively charged atoms. So most elemental atoms, almost all elemental atoms, have to be neutral. But in some cases, they're going to lose or gain electrons. And when they do that, okay, they're kind of tipping the scale between the balance of protons and electrons, okay? So they're tipping the scale so that if you had, say, like 8 here and 8 here, and then you lose one, and you have 7, your atom is now going to be a little bit more positive, okay? So these are formal, full-blown positive or negative charges. So we call anything with a positive charge a cation, anything with a negative charge an anion. I will never test you on that, but it's just good to have an idea of those terms, okay? Now, let's think about why it's important to maybe lose or gain electrons, and it has to do back with that valence shell. So here we've got an atom of sodium. Okay, so you've got one happy shell here, one happy shell here, but one pretty sad shell over here because you're missing about 7 more friends, okay? So this sodium atom is actually like, well, it's going to be really hard to get 7 electrons because they're a hot commodity and I only have one. So maybe it's better if I just donate this 1 electron and then I just have 2 full valence shells. And so it's lost an electron. And that's why it has a slight positive charge, because there's an imbalance now between the protons and the electrons. On the other hand, let's look at chlorine over here. So chlorine has the first shell happy, the second shell happy, and in the third shell, oh my goodness, it's just missing 1 electron over here. So it has 7 out of the 8. And from chlorine's perspective, it's like, I just need that 1 electron. That's all I need to complete my collection. So it's really easy. I really want to get that 1 electron. So I'm just going to take it from sodium. Sodium's ready to give it up to me. So I'm going to take it. And it gets that 1 electron, and that's why it's now got a negative charge, because it gained that electron. Okay? So that's the deal with ions. They basically have an imbalance in the number of electrons they have, so it's more or less, but that's because they're trying to fill their valence shell. Now you might be like, okay, why do they care so much about electrons? It has to do with this principle or idea called electronegativity. The easiest way to explain it is a greed for electrons. So atoms want to seek out electrons. Any atom or element that has a high number of valence electrons, that means they're very close to 8, they are going to have a high electronegativity. They really want to complete that set. They really want to make sure that they get to that number of 8. However, some elements and atoms have a very low number of valence electrons, so close to 1. And because of that, they have less of a desire to fill out that shell, because they have to go and get maybe 7 times the amount of electrons compared to an atom that only needs 1. Okay? So electronegativity is a greed for electrons. And this is a principle we're going to see more of when you're in chemistry, but it's good to kind of keep this in mind. So how do we understand electronegativity? Well, the more you go to the right in the periodic table, the more the greed for electrons is going to increase. So if we look at our elements over here, hydrogen is the least electronegative. Okay, and usually when you are the least electronegative, you're more likely to be positive, and oxygen is the most. Okay? And that's why water is actually a very, very unique, amazing molecule. It's known as a polar molecule. And that's because it's got 2 electronegative elements in it that have these opposite charges. So 2 opposing electronegative elements. Okay? So remember, you've got hydrogen with low electronegativity and oxygen with high electronegativity. Now, I don't want you to think that these 2 are ions, because they have not given up their electrons formally. So polar molecules are technically neutral, but what happens in this case is the oxygen is going to basically kind of borrow the electrons from hydrogen. It's not really going to take it, it's just going to borrow it. So what happens is water ends up with this slightly negative end, and that's what we use as a delta. So it's not a full-blown formal charge like we saw with the ions. It's like kind of negative, okay? And then over here, this is going to be delta positive. So it's slightly positive. Again, these are not as strong as the ions, where it's a full-blown positive or negative, because it's not like it's stolen the electron, it's technically borrowing it. Okay? And this is where we're going to talk about this question in class. So chemistry, it's pretty much the same as human relations, okay? I'm giving you like free dating and friendship advice here. So you're going to think about these types of relations that you have, and what are some characteristics that you would give to them. Okay, now we're going to apply it to chemistry. So atoms, in order to get their desired amount of electrons, they're going to form different bonds. And depending on their needs, there's some different types of bonds that they're going to make. The strongest bonds that takes a lot of energy to break, and it's pretty difficult to break these bonds in living organisms and molecules that they make, are covalent bonds. So in this case, the atoms are sharing the electrons. Okay, so these are the strongest bonds that usually aren't going to be destroyed by heat energy. They require a lot of energy to make, so they're pretty inflexible. This is an imaging of the covalent bond, and the blue area kind of shows where the electrons are going to be. So you can see they're sort of evenly shared by the two hydrogen ions. The second strongest type of bond you have is an ionic bond, and this is what we see with ions. So just like in the case of chlorine and sodium, I'll give you a better graphic for this one, but in the case of chlorine and sodium, chlorine has a negative charge, sodium has a positive charge, so they're going to be more attracted to each other. So the low electronegative elements will give their electrons to those high electronegative elements, because remember, these guys are the ones that are really greedy for the atoms, for the electrons, and these have less greed. Okay? The whole rule of opposite attracts will explain ionic bonds. So they're the second strongest, and that's because they have this unequal sharing of electrons. Okay, compared to over here where it was more equal, these are less equal, so that's why they're less strong. And then finally, the weakest type of bonding we're going to look at is hydrogen bonding, which is what occurs with polar molecules. So this is going to be between molecules, right? The other ones were in the molecules. This is in between the different molecules. So hydrogen bonds are weak bonds that are going to form between the slightly positive and slightly negative end of the molecule. So we see this with water. Okay, so oxygen, that slightly negative end, is going to attract the slightly positive hydrogen end of another water molecule. So these guys are weak individually, but they are strong in number. Okay, so strong in large numbers. And that's why, even though hydrogen bonding is really weak between certain molecules, overall it gives water some pretty amazing properties that we are going to examine more closely at the end of the week. Thank you guys. Bye.